Hi everyone. Today let's talk about Chapter 5, Integration. 5.1, Approximating Area under Curves, and 5.2, Definite Intervals. Big idea. Sums are an important topic to review in preparation for the geometric concepts of an integral as the area under a curve. The area under a curve can be numerically approximated by dividing the area up into thin vertical rectangles of uniform width and of height determined by the y value of the curve, and then summing the areas of all the rectangles. More rectangles of smaller width results in a better approximation. In the limits of an infinite number of rectangles of infinitesimal width, the sum is exactly the area under the curve. Big excuse. You should be able to compute any given sum. You should be able to approximate the area under a curve by dividing up an interval into rectangles of equal width, computing the height of each rectangle using the given function, and then sum the areas of the rectangles to get your numerical approximation. So let's start with the area of some common geometric figures. We know that the area of a rectangle is length times width. What's the next one? Maybe how about parallelogram? Okay. So for parallelogram, we have the base and height. Okay, how do we calculate it? Well, okay, let me go back. Okay, so how do we calculate it? So we know we cut these pieces and move it here. So then we have a rectangle. So that's why the area is base times height. And then the area of a triangle. So if we make one more copy of the triangle, we actually get a parallelogram. So the area of a triangle is half of the area of the parallelogram, which is b times h. How about in general for a polygon? We can divide the polygon into many triangles, and then we can add up the areas, okay? However, it isn't easy to find the area of a region with curved sides. Okay, so such as this picture. So methods to evaluate the area of the region as we first approximate it by the rectangle. So we cut this region into, we divide it into those pieces, and then for each pieces we approximate it using a rectangle. Okay, then we can add up the area of those rectangles and use that area to approximate the area under the curve f of x bounded between x equals to a and x equals to b. And when we let the number of the rectangles goes to infinity, the approximation will be closer, closer, and closer. Okay, so let me show you on our course website. You see this extra credit projects, GeoGebra projects. So let me introduce the second GeoGebra project. Use the GeoGebra to approximate the integral. So when you click the PDF instruction, you can see you can download the GeoGebra, or you can just open it online and then watch this YouTube video to learn how to use GeoGebra to approximate definite integral. And then step 3, I give you step-by-step screenshots, and then you can follow the pictures and then make a GeoGebra project. So once you are done, you can share your projects to public, and then you will get a link. Please email me the link. Okay, so let's see the projects. Okay, so the first one is here. Okay, so you can see n is the number of rectangles. So when n is changing, okay, when it's going more and more, you can see so the upper sum is we use the upper values of the each interval, okay, to approximate it, and where the lower sum where the lower sum we use the lower value to approximate it. So you can see the upper sum is bigger than the lower sum, and the integral is bounded between by them. Okay, so when we increase the number n, the number of rectangles, you can see those numbers getting closer, closer, closer. And you see, this is so close. All right. Okay, that's the first example. And then next example, we have this picture. Same thing, we want to calculate the screen area. Okay. So when we let n goes, you can see here, the upper sum is the pink area, and then the lower sum is the green area, and the integral is the orange area is bounded between them. Okay, and when we increase the number of the rectangles, you can see those numbers getting closer, 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 closer. So very close, right? And then one more example here. Okay, so you can see the pink area is the upper sum, the green area is the lower sum, and then the orange area is the integral. Okay, so you can see when n increases, our answer getting closer, closer, closer to the true value, the integral. Okay, so this is the idea. Let's continue. All right, so let's look at example. Use 4 rectangles with part A, right endpoint, part B, left endpoint, part C, midpoint, to estimate the area under the parabola x squared plus 1 from 0 to 2. First of all, we need to know how to draw, how to graph this function. Well, x squared plus 1, because it's degree 2, so we know it's a parabola. So, and when we plug in 0, 0 plus 1 is 1, so it passed through the point 0, 1. And when we plug in 2, we get 2 squared, which is 4. 4 plus 1 is 5, so we have it pass through the point 2, 5. Okay? And you can see the green area is our region, right? We want to find that area, and we want to divide it into 4 rectangles. So let's use some. Okay, so let's divide it into 4 pieces. 4 equal width pieces. Okay, so you can see each piece is 0.5. That's the width. Okay, so part A, we want to use the right endpoint. So here for the first piece, we use the right endpoint. So that's why the height is f of 0.5. And for the second rectangle, you can see the height is f of 1. And then the third one, the height is f of 1.5. And then the last one, the height is f of 2. So what is that area? For the first rectangle, we have width. The width is 0.5, so that's the width, times the height, f of 0.5, plus 0.5, that's the width, and then the height is f of 1. The third rectangle, the width is 0.5, and the height is f of 1.5. And then the last one, the width is 1/2, and then the height is f of 2. Okay, so then we plug this into our function f. F is x squared plus 1. So f of 1/2, 1/2 squared, which is 1/4. 1/4 plus 1 is 5/4. And then f of 1, 1 plus 1 is 2. Right? And then f of 3/2, well, 3/2 squared is 9/4 plus 1, 9 plus 4 is 13. So 13/4, and then the last one, 2 squared is 4, 4 plus 1 is 5. And then when we add them all up, we get 5.75. Okay, so this is part A. We use the right endpoint sum. So that's why we use R to denote right endpoint sum. Okay, for part B. So for part B, we want to use the left endpoint. Okay, so that's why for the first rectangle, the height is f of 0. The second rectangle, the height is f of 0.5. And then the third rectangle, the height is f of 1. And then the fourth one, the height is f of 1.5. So that's why the left endpoint sum, L4, the first rectangle width is 1/2, height is f of 0. Second rectangle width is still 1/2, the height is f of 0.5. And then the third rectangle, the width is still 0.5, the height is f of 1. And then the fourth one, the width is 0.5 and the height is f of 1.5. And then we plug those numbers into our function. F of 0 is 1, f of 1/2, oh, we already calculated, right? So it's 5/4, and then f of 1 is 2. F of 3/2 is 13/4. And then we put those into our calculator, we can get 3.75. You see, 3.75 is less than 5.75. And because, look at our picture, the area in part A is bigger than the area in part B. So that's why 5.75 is bigger than 3.75. And our actual area is bounded between them. Okay, so part C. So part C, we use the midpoint. So midpoint for the first rectangle, the height is f of the midpoint, which is 0.25. And then the next rectangle, midpoint is 0.75. And then the next, we have 1.25. And then next, we have f of 1.75. So that's why the midpoint sum, the first rectangle width is 1/2, height is f of 0.25 is actually 1/4. And then the second one, width is 1/2, height is f of 3/4. The third one, width is 1/2 and the height is f of 5/4. The last one, width is 1/2 and height is f of 7/4. So we plug it into our function. 1/4 squared is 1/16. 1/16 plus 1, 17/16. F of 3/4 squared is 9/16. 9 plus 16 is 25. So 25/16. And then 5/4 squared, 25/16. 25 plus 16, 41/16. Last one, 7/4 squared, 49/16. 49 plus 16 is 65. So plug this in our calculator, we get 4.625. And it lies between them. And it makes sense because the midpoint, you can see that area, part C, is like between the area of part A and part B. So this is how we can use our rectangles, the area of the rectangles, to approximate the area under the curve. Okay. So definition, the area A of the region S that lies under the graph of a continuous non-negative function f is the limits of the sum of the areas of the approximating rectangles. Okay, so here let's use the right endpoint sum. Okay, so let's use the right endpoint sum. So this is the right endpoint sum. Okay, so what is that? Well, okay, so we want to divide the interval from A to B into n equal subintervals. Okay, so how does that work? Well, we have the interval from A to B. Well, then we want to divide it into n subintervals. Then A is then x0. And then we have x1, x2, and then this is x sub n minus 1, and the b is x sub n. Okay, and what is the width? Well, the width, the change of x is the length of the interval b minus a divided by n, because we want to divide it into n pieces, right? So that's why the width is change of x, and then the area of the first rectangle is f of the right endpoint. So the right endpoint is x1. So that's why for the first rectangle, the height is f of x1. And the second rectangle, the width is still change of x, but the height is f of x2. And then until the last rectangle, okay, the width is still change of x, but the height is f of xn. So that's why we get this formula, okay? The area of the first rectangle is f of x1 times change of x, plus the area of the second rectangle, f of x2 times change of x, plus dot dot dot. The area of the nth rectangle, which is the last rectangle, is f of xn times change of x. And we let n goes to infinity. You can see from our GeoGebra project, when n goes to infinity, actually that limit is the area under the curve. Okay, so here we have some remark. First, in fact, we can pick any point xk from the subinterval x sub k minus 1 to x sub k. So we don't need to pick the right endpoint. We can pick any point. Okay, so let's say the first interval, we pick this point x. Let's call it x1 star. And for the second interval from x1 to x2, let's pick the point x2 star. Okay, so x sub k bar is actually a point, any points with lines in that subinterval. Okay, and then this sum, the sum of the rectangle of those, okay, is called Riemann sum for f on the interval a to b. This sum is a left Riemann sum if the point we pick is the left endpoint of the interval. This sum is called right Riemann sum if the point we pick is the right endpoint of each subinterval. It's called midpoint Riemann sum if we choose the midpoints. Okay, and it can be shown that we'll get the same value if we use any Riemann sum. So that's why from now on, we just use the right Riemann sum to calculate. Okay, so that's why from now on, we use the right Riemann sum to calculate. Okay, and so here we have some useful formula. Okay, so the first formula, so I would say the first formula is sum of 1, where I goes from 1 to n. Okay, what does that mean? Oh, that's 1 plus 1 plus da 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 plus 1. And how many copies of 1? There are n copies. So what's the answer? That's n, right? The second one, maybe let me use the index to be k instead of I, so that I can be consistent with what we're going to talk about later. Okay. All right. And then the second formula, we have sum k from 1 to n of k. You see, when your index, when your k start with 1, you get 1. When k increase, you get 1 plus 2 plus 3 plus da da da. The last one, you plug in k equals to n, right? And what is this guy? Well, how do we get n times n plus 1 over 2? Well, for this guy, I can actually prove to you. Okay, so I can prove to you. So let's say this is S. So S equals to 1 plus 2 plus 3 plus da 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 plus n. Let me write one more term. The previous term is n plus 1. The last term is n. Okay. Now I'm gonna reorder them. So I put n here and n minus 1 next and n minus 2 next plus da 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 plus 2 plus 1. Okay, I just reorder from the biggest to the smallest. So now let me add those together. Now you see what happened? N plus 1 is n plus 1. This guy is also n plus 1. This guy is also n plus 1. This guy is also n plus 1. This is also n plus 1. So we have n plus 1. How many copies of those? N copies. So that's why S equals to n times n plus 1 over 2. So that's why we come up with this formula. Okay, so I have shown you that. How about sum of k squared? So what is sum k from 1 to n of k squared? Well, when we plug in, we get 1 squared, 2 squared, 3 squared, n squared. Well, that is, the formula is n times n plus 1 times 2n plus 1 over 6. Okay, so that's the formula. How you need to memorize those formula. How do I remember this formula? Okay, I remember the basic one. You start with n, you count up, right? N and n plus 1, and you divide it by 2. Here, it's similar as before, but you have an extra factor, which is 2n plus 1, and then you divide it by 6. Okay, the next one, sum of k from 1 to n of k cubed. That's 1 cubed plus 2 cubed plus n cubed. This guy is actually, you can see this guy is actually this guy squared. Right? It's n squared, n plus 1 squared, 2 squared is 4. So this is how I remember it. Remember the first one, n times n plus 1 over 2. And then the third one, the k cube is going to be that one, that formula squared. So n squared, n plus 1 squared over 4. And then for the sum of k squared is n times n plus 1 times 2n plus 1 over 6. Okay, so this is how I memorize it. Alright, so do you remember that in chapter 3 when we learn about derivative, we have 3.1, we use the limit definition to find the derivative. Okay? And here similar. We can find the definite integral by definition of Riemann sum. Okay? So in that case, you cannot use the antiderivative formula. You have to prove it using this method, okay? Prove by definition of Riemann sum. And here are the procedure. First, we're going to partition the interval a to b into n subintervals. So if I can, maybe it's good to draw the picture, then it can help you understand. Okay, so a, remember that's x0, x1, x2, b is x sub n. Okay, so we divided our interval into n subintervals. Then the change, so the width change of x is b minus a, the length of the interval, over n. Okay, so that is the first step. We partition the interval into n subintervals and find the width. Second step, find the right endpoint sum. Okay, find the right endpoint. What is the right endpoint for the first guy? Well, what's the relationship between x1 and x0? You can see x1 is like x0 plus change of x, right? Well, x0 is a, so x1 is a plus change of x. How about x2? Well, x2 is like x1 plus change of x. So this is like a plus 2 times change of x. So you can see, how about x sub n? Well, x sub n is then a plus, see, it was 1, and it's 1 change of x. If it's 2, then it's like 2 times change of x. If it's like n, then this is like n times change of x. That's why all the right endpoints, x sub k is a plus k copies of change of x. Okay, so keep that in mind. That is the second step. The third step, the right Riemann sum, is the sum of the area of the rectangles. What's the area of the rectangles? Height times width. Okay, well, what's the height? F of x sub k. X sub k is, we use the formula in part 2, a plus k times change of x. Okay, and then we plug it in, and then we can expand it using the formula of f. Then you're gonna simplify, use the above formula. The above formula are these. Okay, they'll be useful. We'll work on an example later. You can see how we use it. Okay, so eventually you will get a formula of n. Then last step, let n goes to infinity, then you can get either infinity or a number. Okay? All right. So let's follow those 4 steps and work on this example. First step, what is the interval? Okay, so first step, we want to partition the interval 0 to 2 into n sub interval. Okay, so let's draw a picture here. We have 0 and 2. We want to cut it into n sub interval. So this is x0, this is x1, x2, this is x sub n. Then change of x. What's the change of x? Is then b minus a, so 2 minus 0 over n. So that is 2 over n. Okay, so that is the first step. Step 2. What is the right endpoint? So x sub k is the starting point, the initial point a, plus k copy of change of x. Well, a is 0, so 0 plus k, change of x from part 1, so from step 1, that's 2 over n. Well, so this guy is 2k over n. That is the right endpoint. And then the third step, we want to write the right Riemann sum. Well, that is the sum of the area of the rectangles. So k from 1 to n. The area of the rectangles is the height, f of x sub k, the width, change of x. Okay, so what is x sub k? By step 2, that's 2k over n. Okay, so, and change of x, or change of x is 2 over n. So far, so good, everybody? Okay, so you can see this is a sum about k. Well, then 2 over n, it has no k in it. So this is like a constant. So because it's a constant, I can move it outside. Okay, I can move it in front of the sum. So we get 2 over n, and then we have the sum k from 1 to n. And what is f of 2k over n? Well, that means you're going to plug this into the formula of f. Well, f is 5x cubed. So whenever you see x, replace x by 2k over n. 5x cubed plus 4x squared, so 2k over n squared, minus 7x, 2k over n, plus 3. See, this is f of 2k over n. Now let's simplify it. So how do we simplify? Okay, so let's see. So 2k over n cubed, let's split. Okay, we got 2 cubed is 8. We have k cubed and over n cubed, right? And then the next term we have 4. 2 squared is 4 and k squared over n squared. Minus 7 times 2 is 14. 14k over n plus 3. Okay? So we move the exponent into each of the factors. Okay, so what do we do next? So here, I want to distribute the sum. Okay, so how do I distribute the sum? So when I distribute the sum, we have sum k from 1 to infinity. Okay, so I want to group the 5 and 8 over n cubed together. And I want to split the k cubed. Okay, and then plus the sum k from 1 to n, 4 times 4, 16 over n squared, and I have k squared. Okay, minus, and then we have the sum k from 1 to n, 14 over n times k, plus the sum k from 1 to n of 3. Okay, what do we do next? Let's continue and simplify it. So we can move all the constant. So here, all these are constant multiple. I can move it in front of the sum. Okay, so this is constant multiple. I can move it in front of the sum. Constant multiple, move it in front of the sum. So the first one, we get 5 times 8 over n cubed. And then we have sum k from 1 to n of k cubed. The next term, we have 16 over n squared, and then we have the sum k from 1 to n of k squared. Next, we have 14 over n, and then we have the sum k from 1 to n k. Plus, you can think of, see, this is sum of the 3. So we're adding 3. We have n copies of 3 adding together. So that's why sum of a constant. You can also think of this as you move the sum in front, then it's only 1 left. So we have sum k from 1 to n of the 1. Okay, now you can use our formula. What other formula? Okay, so we have 2 over n stay there. 5 times 8 is 40. Sum of k cubed. Okay, see? This guy, I can use the formula. This guy, I can use the formula. This guy, I can use the formula. And this guy, we can use the formula. Sum of k cubed is n squared, n plus 1 squared over 4. Sum of k squared, do you remember? n plus 1, 2n plus 1, all over 6. And then the next term, we have negative 14 over n, sum of k, n plus 1, all over 2, plus 3, sum of 1 is n. Okay? All right, so what happened? You can see here, we can now distribute the 2 over n. Okay, then the first guy becomes 2 times 40 n squared, n plus 1 squared. The bottom, we have 4n to the n times n cubed is n to the 4. And when we distribute, we have 2 times 16 and n plus 1 to n plus 1. And the bottom is n times n squared, so n cubed, and then we have 6 there. Okay, so we are distributing. Let me write it down. So we're distributing. So we use this guy multiplied by that, this guy multiplied by that, this guy multiplied by this guy multiplied by that. Okay, we distribute. Okay. All right, let me see. Let me move down a little bit. Oops. Okay. All right. Let me move this equal sign down a little bit. Okay. Looks good. And then we continue to distribute. Okay. So we have 2 times 14 and n plus 1. The bottom, we have n squared, and there's another 2. The last one, 2 times 3n over n. Okay, so this is Rn. You can see. So this is n to the 4. So you can see for each term, what's the degree of the numerator? Well, this term, the degree of numerator is 4. And then the degree of denominator is 4. This guy, the degree of the numerator is 3. And then the degree of the denominator is also 3. You can see for each term, the degree of the numerator equals to the degree of denominator. So that's why when n goes to infinity, so the area equals when n goes to infinity, we just look at the dominant term, right? So that's why here, what is the dominant terms? The dominant terms are 2 and 40, n squared and n squared. Okay, okay, I don't want to make too much. Okay, so n to the 4th. The bottom is 4n to the 4th. And the next one, the dominant term is 2 and 16, n. 2n. So n, 2n over 6n cubed. The next term, dominant term, 2, 14, n, and bottom 2n squared. And then, oh, here, n cancel, we get 6. Okay, you can see all those n's cancel. And then let's look at the ratio. The first one, 4 cancel, so 20. And then the second one, you can see this 2 and this 6 cancel, we get the 3. So that's why we have 2 times 16 is 32 over 3. Minus, here 2 cancel, we have 14 and then plus 6. Okay, so let's plug this in our calculator. 20 plus 32 divided by 3 minus 14 plus 6. The answer equals to 68 over 3. Okay, if you want to use decimal, that's approximately 22.66666, so 6 repeated. So far, so good. So that is the area under this polynomial on the interval from 0 to 2. Okay, and the first steps, we partition the interval into n subintervals, and then we figure out the width change of x is b minus a over n. And then we compute the right endpoints, x sub k. And then the right Riemann sum is the sum of f of x sub k times change of x. And then we figure out what's x sub k and what's change of x, plug it in. And then what is f of 2k over n, plug that into our function f. Okay? And then we're gonna do a lot of algebra. We split the factors and move the exponents. Okay, distribute the exponents, and then we're gonna distribute the sum. Okay, because when you sum a bunch of numbers, you can choose to sum number first and choose to sum the sum number, and then you add up together. Okay, so sum is addition is commutative and associative. Okay, and then for the constant multiple, you can move it outside of the sum. So, and then we can use our formula of sum of 1, sum of k, and sum of k squared, sum of k cubed, and plug it in. Okay, so we will get a formula about n. Eventually, you're supposed to get all the terms. The degree of the numerator equals to the degree of denominator. So then when n goes to infinity, you will get a number for all of these terms. Okay, so if you're given a polynomial function, that's what happens. Okay, so let's continue on example 2. Okay, evaluate the definite integral by the method of Riemann sum. So which is the same thing. Okay, because the area under the curve bounded by here is bounded by 0 to 3, right? So We have 0 to 3 here. We divide it into n sub pieces. x0 is 0, x1 here, 3 is x sub n. First step, we're gonna partition the interval, so 0 to 3. So I really hope that you can pause the video and try to work on this problem first, okay? And then after you're done, you can continue to play the video and check your answers. So partition the interval into n intervals. And then change of x is then 3 minus 0 over n, which is 3 over n. So second step, what is the right endpoint? Well, the right endpoint is x sub k. Well, that is a plus k copies of change of x. A is 0, k copy change of x is 3 over n. So the answer is 3k over n. And the third step, what is the right Riemann sum? Well, that is the sum of k from 1 to n, the area of rectangle, which is the height, f of x sub k times the width, change of x. Okay, let's put it in. F of x sub k is 3k over n, and the change of x is 3 over n. Because 3 over n has no k in it, so it's like constant multiple, we can move it in front of the sum. And next, let's expand it. So plug it into our f. What is our f? That is our f. So 3 over n, and then we have the sum k from 1 to n. So 2x cubed, so 3k over n cubed, minus 5x squared. So 3k over n squared plus 9x 3k over n minus 11. Okay, so let's expand it. So let's see. Okay, so here I'm gonna increase the speed. Okay, so I'm gonna expand it, and at the same time I distribute the sum and move the constants in front. So the first term, we have 2 and then 3 cubed over n cubed. Okay, then we have the sum k from 1 to n of k cubed. Is that okay, everybody? So we distribute the exponents 3 cubed, k cubed over n cubed, but 2 times 3 cubed over n cubed is a constant. We can move it in front of the sum. And then the second term, we have 5. When we distribute the power, we get 3 squared and n squared. And we can move it in front of the sum as well, because this is a sum about k. As long as the expression has no k in it, then it's like a constant multiple. We can move it outside. Next one, 9 and 3 over n, and then we move it in front of the sum, so we have k. And then 11, when we move 11 out, it's like 1 left. So far, so good, everybody. Okay, let's continue. So now we can use our formula. So we have the formula, sum of k cubed, sum of k squared, sum of k, and sum of 1. Let's plug it in. Do you remember what is that? So I hope you can remember. So here 2, 3 cubed over n cubed. That is n squared, n plus 1 squared, all over 4. Next, what is that? That is n plus 1, 2n plus 1, all over 6. Next, 9 times 3 and Sum of k is n plus 1 over 2. Sum of 1, n. Yes. Okay, what's next? We're gonna distribute it. So distribute, there are 4 terms. Okay, so we distribute the 4 terms. First term, what do we get? So you can see 3 and 2, 3 cube n square n plus 1 square all over n times n cube n to the 4 and 4. That is the first term. Second term, 3 times 5, 3 square n plus 1, 2 n plus 1 denominator, n times n square n cube times 6. The next term we have 9 times 3, so 3 times 9 times 3, n plus 1 over n times n squared times 2, minus 3 times 11n over n. Ooh, n cancel. So let's check. You make sure you see each term, the degree of the numerators equals to the degree of the denominator. So that's always the case when you integrate a polynomial. Okay, so in the exam, in the final exam, when I ask you to evaluate a definite integral by the method of Riemann sum, I will always give you a polynomial up to degree 3. So those you're gonna expect similar problem, just like the coefficient will be different. Okay, but you use the same steps. Alright, so that is Rn. Step 4. Let n goes to infinity. That means you just need to look at the ratio of the leading coefficients. So the limit, the area is the limit, n goes to infinity of the right Riemann sum. So that is the first guy. See? What's the dominant term of the first guy? Well, I see 3 times 3 cubed, so 3 to the 4th. That is 81. And 2 and 4 cancel, so we have 2 down there. And then you have n to the 4th and n to the 4th there. So actually they can cancel later. Next term, 3 and 6 we can cancel. We get 2 down there. And then the top through 5 times 9 is 45. Over 2, and then oops, you look at the dominant term n and 2n. So this is a common mistake. A student forget the 2 there. So that's why this 2 will cancel with this one. Next term, 3, 9 times 9, 81. So 81 n squared over 2n squared. N squared cancel. And here the n's cancel as well. And then minus 33. Okay, now let's see what happened. We have 81 over 2 minus 45 plus 81 over 2 minus 33. Okay, so put this in our calculator. By the way, this guy add together, we just get 81 because there's 2 copies of that added together. So 81 minus 45, and then minus 33. The answer is 3. Oh, so 3 is our final answer. Okay, so far so good. Do you get the same answer? Let's continue. So example 3 approximates the area of the region under the graph of f of x equals to cosine x on the interval from 0 to pi over 2. Okay, write an expression. Do not evaluate the limit. Okay, so this is our interval. This is x0 and then x1, x2, ... This is x of n. Okay, so the 4 steps. First, we're gonna partition the interval from 0 to pi over 2 into n sub-intervals. Okay? Then change of x is b minus a, which is pi over 2 minus 0 over n. Wow, That's pi over 2n. So far, so good, everybody? And the second step, the right endpoint, x sub k is then the initial point 0 plus k copies of change of x, so pi over 2n. Oh, so that's k pi over 2n. The third step, the right Riemann sum, is the sum k from 1 to n area of rectangles is the height f of the x sub k times the width, change of x. F of x sub k is f of k pi over 2n. Change of x is pi over 2k. So because this is a constant term, we can move it outside. Constant means it has no k in it. K is like the variable. It changes from 1 to n. Okay, so that's pi over 2n and the sum k from 1 to k. F is cosine x. X is k pi over 2n. So however, we get stuck here because we don't know how to split the cosine, okay? Actually, we can't. Unlike what we did for polynomial, we can split it, and then we know sum of 1, sum of k squared, sum of k cubed. But here, the cosine k pi over 2n, we don't know what is that. So we have to, that's why this problem only asks us to write an expression. Do not evaluate the limit. So A is the limit of y and the right Riemann sum. So it's the limit pi over 2n and the sum k from 1 to n cosine k pi over 2n. Okay, so this is our answer. Write an expression. Do not evaluate the limit. So far, so good. So that's why if I give you a problem in the exam and ask you to compute, you're actually only able to compute the definite integrals for polynomials. So that's why I tell you that I will ask you the problem that is polynomial degree up to 3. Okay, so you're gonna expect a problem like this in the exam, final exam. Okay. All right. So let's conclude. General Riemann sum. So what we have done is we divide the interval into n subintervals. What happens if we don't divide it into n equal with subintervals? Okay, so in general, we can divide it into n subintervals, but they don't need to be the same width. Okay, so let change of x sub k be the length of the subintervals x sub k minus 1 to x sub k, and let xk bar to be any points within that interval. Okay, then what is the sum? The Riemann sum is f of x sub 1 bar, okay, times the width of the first rectangle, change of x1. And then the second rectangle, the area is the height f of x2 bar, and times the width is change of x2, plus ... The last rectangle, the width is change of xn, and the height is f of xk bar. Okay, so this is called a general Riemann sum for f on the interval AB. Okay, so definite integral. If f is a function defined on a closed interval, then the definite integral of f from a to b is a number. Okay, so the definite integral from a to b of f of x dx, that is the limit. So here we know it's the sum of those it's the sum of the area of those rectangles. And before because we have equal width, we can let n goes to infinity, and that's it. But right now we don't. Letting n goes to infinity is not enough. We actually need to let all the change of x goes to 0. So you get more tiny subintervals. Okay? So because here we say let the maximum So the maximum change of x sub k goes to 0 because the biggest guy goes to 0, then which means all of. So this is the same as saying all of change of x sub k goes to 0. Okay, and that is the general Riemann sum. And why do we need that? Why we cannot just say so why not just use the limits angles infinity of that? Okay, well, the answer is, well, let's say you have like this. Okay, so this is A, this is B. Well, you can just if you just let n goes to infinity, I can have my change of x1 just stay the same, and then I can let the rest be smaller. Then the n still goes to infinity, but however, you can see now my area is never be equal. So that's why you not only let n go to infinity, you also need to require all the width of the subintervals goes to 0. Okay, that's why we say, oh, the biggest guy goes to 0, then which means all of them goes to 0. Okay, so this is a definite integral provided this limit exists. If it exists, we say the function f is integrable on the interval a to b. And a, b are called the limits of integration. F of x is called the integrand. X is the variable of integration. Okay, so theorem. If f is continuous on the interval a to b, or if f has only a finite number of jump discontinuities, then f is integrable on ab. Well, we allow to have a finite number of jump discontinuity because you can have some picture like this. You can still integrate it, so that that's the integral of this guy plus the integral of that guy plus the integral of that guy. So we still allowed. We don't require it's like always continuous. When it's continuous, then it's integrable. We can also allow a finite number of discontinuities, jump discontinuities. Okay, so next concept, nest area. Consider the region R bounded by the graph of a continuous function f and the x-axis between x equal to a and x equals to b. Well, we see, so what's the integral? The integral is the Riemann sum, right? The limits, so from now on, we can use the right Riemann sum. So that is the limits n goes infinity, sum of k from 1 to n, f of x sub k times change of x. So here, change of x is always positive. So change of x is always positive. But your f, well, it really depends on your sign. If your f is above, then f of x sub k is positive, then you adding a lot of positive sum, your area will be positive, right? But however, if your function is negative, if f is negative, then your this is negative, and then change of x is positive, then your sum is gonna be negative. You're adding a lot of negative numbers, the answer is still negative. So that's why when your function f is below the x-axis, that area is actually gonna be negative. So the net area of the region R is the sum of the areas of the parts of R that lies above the x-axis minus the sum of the area of the parts of R that lies below the x-axis. Okay, so net area is the definite integral. That's the area above the x-axis minus the area below the x-axis. There is another definition about the total area. So what is the total area? Well, the total area is saying, okay, I don't want to be negative area. I want all the area to be positive. So what does that do is they calculate the integral of the absolute value of f of x. What does absolute value do? when it's positive, it stays the same. But when f is negative, it will flip it over on top of the x-axis. So now, see, this guy is now positive. So the total area is the area above the x-axis. Now plus area below the x-axis. Okay, which is the green area. Okay. So the net area, you use the area on the top minus the area below the x-axis, where the total area is you just add them. It's like distance and displacement. Displacements have directions, right? When you fix suppose we have one-dimensional motion, so you fix one direction as the positive direction. Let's say if going to the right is the positive direction. Then when you go to the left, you get negative displacements. But distance, you always add them. So if you let's say the right hand side is the positive direction. If you go right 2 meters and then you go left 4 meters, what is the distance? The distance you travel is 2 plus 4, which is 6 meters. However, the displacement is 2 minus 4, which is negative 2. Okay? So that's the difference between net area and the total area. So we mark if f is integrable on the interval a to b, then our definite integral is actually equal to the right Riemann sum, the limits of the right Riemann sum. And change of x is b minus a over n, x sub k is a plus k copies of change of x. So this is how we calculated the definite integral using the definitions of Riemann sum. Okay, so let's continue in the video part B.